just occurs here. Here's a problem where we have on the left a circle inscribed in a square, and on the right a square inscribed in a circle. We're asked to decide which of these two has the largest proportion of its area shaded. So let's have a look at the first diagram. Circle inscribed in a square. Now you might be wondering how on earth I can even begin this, because there are no measurements. However, we're asked for what proportion of the figure is shaded. That doesn't matter what size this diagram is, whether it becomes larger or smaller and so on. That proportion will always remain the same. So we're at liberty to choose whatever unit we want. Let's choose a unit that makes sense. Why don't we choose the radius of the circle to be 1 unit? That would make the side of the square 2 units. So the area of that circle, remember the formula is pi times r squared, will be pi times 1 squared. Pi times 1 times 1. That's just pi. So whatever the units are, it'll be pi units squared. That's the area of the circle. Let's have a look at the area of the square. That's not a tricky one. Each side is length 2. So the area will be 2 times 2, 2 squared. That's why we call it 2 squared, because you're finding the area of a square of side 2. 2 squared is 4. So the area of the square is 4 units squared. So the proportion of the square that's shaded is the circle compared to the whole square. That's pi compared to the whole square of 4. So pi to 4. Let's have a look at the next diagram then. This time we've got a square inscribed inside a circle, and again no units, so we're at liberty to choose whatever units we want. We were successful with this radius being 1. Let's do the same. However, if I draw this radius across there, we're missing a vital connection to the square. So let's instead, remember the radius, there's loads of radii all the way around. So let's choose that as a radius of 1, which would mean the diagonal of this square has radius. The diagonal of this square is length 2. 1 plus 1 is 2. And we don't know the side. It's not obvious what the side of the square is in this case. So let's look at the area of the circle. Not much changed from the last one, which we've successfully worked out was pi units squared. So the problem is the square. So you'll notice that we do have a right-angled triangle where the hypotenuse is 2. And Pythagoras' theorem give us x squared plus x squared, that's the sum of the two smaller sides squared, being the hypotenuse squared, 2 squared. So x squared plus x squared, that's a couple of x squareds. 2 squared's 4. Divide both sides now by 2. Now usually we'd take the square root of both sides at this time, but remember we're looking for the area of that square, which is x times x. The length times the breadth, x times x. That's what we've got here. X times x is x squared, and we're told that's 2. So the area of the square is 2 units squared. So the proportion of the circle this time, that's shaded is, well, it's the square to the whole figure this time. So it's the square to the circle. That's 2 to pi. So we've successfully worked out the two ratios or proportions or fractions, that fraction that's shaded. But which of these two is larger? So we're comparing pi upon 4 and 2 over pi. Now it's interesting, I'm not going to use calculator, but if you have a calculator there'd be no trouble, you just work them out and find out which is the bigger one. But suppose we don't have a calculator. We know pi is very close to 3. This is slightly bigger than 3. Now if we increase the numerator of a fraction, let's suppose it was 4 quarters, that's 1. 5 quarters, 1 1/4. 6 quarters, that's 1 1/2. The fraction gets bigger. So if we increase the denominator, that fraction gets bigger. So certainly if we make the denominator smaller, we produce a fraction that would be smaller than pi over 4. So pi over 4 is slightly bigger than 3 quarters. Now similarly, what happens here if we look at pi, 3 point something, if we make that smaller, what happens to this fraction? 2/3, 2 over 2 is 1. 2 over 1 is 2. The fraction values are getting bigger. So if we make this smaller, the value of the fraction is larger. So 2 over 3, we're making the denominator smaller, we're increasing the value of the fraction. It works the other way. This becomes 4, 2 over 4, 2 over 5, 2 tenths, 2 hundredths. The fraction's getting smaller. So as the denominators increase, the fractions get smaller. So 2/3 will be bigger than 2 over pi. And then we're looking at the problem about 3 quarters and 2/3. Which is the bigger of these two? Well, let's change them into 12ths. We can do that by multiplying top and bottom by 3 in the first fraction. That gives us 9/12ths. And multiplying top and bottom by 4 in the second fraction. So we're looking at 9/12ths compared to 8/12ths. And you can see that 9/12ths is greater than 8/12ths. So all in all, we've got a whole series of fractions here, starting with the biggest one, and this gets smaller, and this gets even smaller, and this gets even smaller than that. So we've got pi over 4 being greater than 2 over pi. So which diagram has the greater area shaded? So the square has the greatest fraction of it shaded, proportion shaded. Now that's not the only way to make that argument. There's a beautiful little deduction, and you wonder, how on earth do I know to start with pi squared and 8? Well, look at these two. Sometimes in fraction work you look at these opposite numbers, pi times pi and 4 times 2, pi squared and 8. Pi is bigger than 3. 3 squared is 9, so pi squared is definitely greater than 8. Let's divide both sides by 4 pi. And that'll still be greater than, because 4 pi is positive. So look at this fraction. We take a factor of pi times pi on the top line. One of them cancels with this pi on the bottom line, so we get pi over 4. And a factor of 4 on the top line, 8, is 4 times 2, so the 4 factor cancels with this 4. We're left with 2 over pi. So again, the same conclusion as we had before. So that's Mr. Corsi signing out, and hope you enjoyed the video.